How are
sir.
you there?
Okay, good. It said I didn't have permission to go voice, but anyway.
Yeah,
Okay, I'm
great.
here.
Hey, thank you so
Yeah.
much for coming to this AMA. My name is Zach ZYZ. I'm going to be asking the questions from the people here at the Discord, and I'll give you a little intro and everything there.
Okay.
So thank you to everybody who participated and joined in this discussion. This is Lawrence Krauss. He is a theoretical physicist and cosmologist who previously taught at ASU, Yale University, and Case Western Reserve University. I believe that he has a brand new book that's coming out called The Physics of Climate Change. I'd definitely like to hear what it's all about.
It's actually out already.
It's out already? Oh, shit.
Mm-hmm.
All right, well, fantastic, right there. So first, I want to thank you for just agreeing to come and take some of our questions. I understand you only have about 45 minutes here, so I'll try to keep things at a pretty solid pace. And all right, let me go to, so this is a question that was sent to me by Relay. I'm going to ask one question, and then Chad King has a question that he'd like to ask. And this is actually, this came from Hito Pepe right here. And he asked me a question. One of his roommates passed this question on to him. He said, if I could ask Lawrence Krauss something, it would be his thoughts on the once we see it, then it's too late theory solution to Fermi's paradox. So,
Okay. Well, look, I mean, so let's make it clear for everyone what Fermi's paradox is supposed to be. It's Fermi basically asked about aliens and said, if they're out there, how come they're not visiting in some sense? Because it is true that if aliens were out there and had been around here, the universe for the last 5 billion years, they would have had time to expand beyond their home planet if that was their inclination. And of course we don't see that. Now, there are lots of solutions to Fermi's paradox. I don't know what is the simplest one. I think the point is that it's not clear that a civilization has an imperative to quickly move beyond its surroundings if its surroundings are pleasant. We'll see how long it takes humanity to expand beyond the Earth. But if you look at the history of the Earth, people didn't really en masse leave North America until there was, until it became unbearable for them. Physically, they could have. It was physically possible for boats to have taken people from one part of the world to the other, but they didn't do it for a long time, and except for random accidents. So it could just be that there's no priority in quickly colonizing the galaxy if you've got a place that's pleasant. I actually think there are two other arguments that suggest why this doesn't happen. Besides the fact that, let's face it, it is daunting and incredibly resource intensive to consider ever taking a spacecraft outside of its local surroundings. I mean, the requirements to travel in space are just immense, and the likelihood of doing it successfully is very small with anything but a microscopic, very small satellite, or it's a very small object that you could transport on a light spacecraft. Living beings are not the best way to travel throughout space. But beyond that, I think there are two arguments. One is that it's quite likely if there was a very advanced civilization, it would have no. What's the point? What can be gained? What's the? They're not going to get anything out of trying to explore and see and find lesser life forms, especially since they probably know they exist, and so therefore the only scientific value would be to learning what kind of life forms exist. But if they're intelligent enough, they've been able to determine those things. So they may turn inward. They might just say, we're not interested in exploring. The other possibility, which I think may be even more likely, is that intelligent civilizations don't last that long. If you look at life on Earth, it's not clear how we've had a technological civilization. You pick your time, a few thousand years, a few hundred years. And it's not clear how that's going. And so the Fermi's paradox really requires a civilization to be incredibly long-lived and desirous of exploring and desirous of taking the resources to explore, none of which may be necessary. So I've never really thought it's much of a paradox. The galaxy is extremely big and extremely difficult to travel across, and you can't do it with spacecraft that are traveling anywhere near this, even anywhere near the speed of light. So there's long, slow voyages, and there's just so many things that can go wrong in the way.
Absolutely. All right. Yeah, that's a great answer. Thank you very much. So, Chad, are you there in the chat?
I am.
Okay, so Chad had a question he wanted to ask you directly. Chad, what's your question, please?
Okay. So, given quantum non-locality and other non-local phenomena like gravity and electromagnetism, is space even real, or is it like just an illusion?
Well, let's step back and parse what you said. Quantum mechanics appears to have non-locality if you think of it classically, but gravity and electromagnetism are quite local. They're not global. They depend on the exchange of particles, literally. So that, for example, if the sun were to disappear now, we wouldn't know about it for 10 minutes because gravity propagates at the speed of light, as does electromagnetism. So it's not local at all. It's not global at all. It's extremely local. It depends on that, on what's happening locally and that propagating out, and we can calculate the rate of propagation, and it happens to be the speed of light. So, so that's important to correct your question that way. In terms of whether space is real or not, I think I think you can ask yourself the question whether do you find a difference walking into a wall or opening a door and going outside. It seems pretty real to me. Quantum mechanics has certain kinds of non-locality which can be manifested by very careful and special experiments that are done to preserve quantum mechanical correlations that otherwise disappear classically. So the apparent quantum non-locality is really just a classical way of picturing an underlying phenomenon, which is explained. Quantum mechanics is also a local theory. The Schrodinger equation is a local theory for what happens to the wave function, but and it's causal and all the rest. It's just the manifestation of it classically appears to be non-local, which you can exploit if you carefully prepare experiments. So if you ask me, I'd say, yeah, space is real, time is real, and we might as well act as if they're both real.
Okay, fantastic. Thank you, Chad, for your question. So Mighty Thor, who was instrumental in helping organize this whole thing, thank you very much. So Mighty 494 asks, would a violation of the conservation of quantum numbers mean a destruction of quantum information? And he goes on, why is gravity so hard to quantize? And what do you think about the public's policy towards climate change? So whatever piece of that is most interesting to you, just sink your teeth into it and ignore the rest.
Yeah, there's a lot of questions there. Well, look, I think that I'll answer the first. I'll try and remember them in order, but it's true that quantum mechanics are what are called quantum numbers, which describe the state you're in, and there in quantum mechanics, those things are preserved in a sense. The state of a system is preserved unless there are interactions, and you can follow those things. So information is preserved. But as Hawking was one of the first to point out, if material falls in a black hole and you lose information about what state it's in, and then the black hole disappears, you've lost information. And that was a real paradox, which is really still not fully resolved. Lots of people have made arguments about how that information may escape the black hole in its evaporation, and so it might not be lost. I'm not convinced we really have the perfect answer to that question. There's tentative responses. So, but if it really was true, then yes, and a fundamental tenet of quantum mechanics would be violated by black hole evaporation, which does reflect one of the problems of gravity and quantum mechanics. The real problem of gravity and quantum mechanics is more subtle, perhaps, and that is that gravity as a theory ultimately becomes very, very strong at very small distance scales. And if it's a quantum theory, then on small distance scales, you should be able to calculate quantum corrections, quantum phenomena. But when you try to, in the context of general relativity, just treating it naively as you might quantize electromagnetism, as we do to create quantum electrodynamics, if you use the same kind of prescriptions, then you find that the number things go out of control. There are infinities that you can't get rid of, and basically you can't make sense-well predictions. The theory just doesn't allow sense-well predictions, And that's the technical problem with gravity and quantum mechanics. It's, ultimately it comes down to the question of whether space and time are quantized and how they might be quantized. And there are other sort of more general issues about the nature of space time and whether, as I say, whether there's a smallest physical scale, whether there's a smallest time scale. But we just don't have a way right now of dealing with it. String theory was an approach that was developed to try and address that question, and it was well motivated, but it's brought a whole morass of additional intellectual baggage in the process, and it really hasn't yet resolved any of those issues. And it's not yet demonstrated that it actually explains the real world. It requires a whole slew of extra dimensions and lots of other things. Maybe it does. Maybe at some point it will be able to provide us firm predictions, but at the current time it can't. But the problem with quantum gravity is just that gravity, if we treat gravity as we treat electromagnetism and the strong force and the weak force, we try and do the same things for general relativity as a classical theory that we do for electromagnetism, we come up with crazy numbers and the approximations become uncontrolled. Now, I think the last question had to do with climate change.
Yeah,
but I forget what part of that question.
Let me. Actually, he had like a raft of good questions here, and so these may tie in together. He asks, what you thought about current public policy towards climate change? He goes on, do you think that fusion energy will ever pan out? And what do you think that the role of atomic energy should play in society? And all three of these are relatively closely interlinked.
Okay. No, they are. Let me go take them backwards, because it's probably easier to answer them in that order. Nuclear power should be a part of any strategy. Mm-hmm. This fear that the public have about nuclear power is largely misplaced. I mean, there have been bad designs of reactors, but the number of people that have died, even if you take the worst estimates of Chernobyl and Fukushima, you could argue no one. You could argue very small numbers or no one in some cases. And 3 Mile Island, very badly designed reactors. Even taking all that into account, the number of people that have died due to nuclear power is far less than the number that have died due to coal, for example. And so, and with the more intelligent reactor design, as is happening now, and modular design, and they're really not only not the kind of level of danger, but they're a useful tool, especially the ones that have already been built and are running. To shut them down would be I think crazy, because they do provide their carbon. They don't produce carbon dioxide in the atmosphere, and they function. Building new ones is a challenge because there are huge economic issues. But the only arguments against nuclear power right now are large scale economic ones. Whether it makes economic sense to invest that much in a large central facility, that may take 20 years to build versus smaller scale facilities and other things. But people are talking about small scale reactors. So it's certainly worth a part of any approach that we make to reduce the amount of carbon dioxide we're putting in the atmosphere. A part of any strategy, I think, should be the use of recognition of nuclear power as a possibility. I mean, the negative parts of it are, of course, the disposal of waste. But again, that's more of in my mind, a political issue. It's the fact that everyone's so afraid of it that no one's allowing the waste to travel to a place where you could dispose of it. And there are places where you could dispose of it. The other thing, of course, is the possible connection between nuclear reactors and proliferation. But again, if you carefully monitor things, you can ensure that the reactors don't produce products that can be used for weapons. So anyway, bottom line is I think we need to consider we shouldn't rule out nuclear power, and we shouldn't randomly close down plants because of just
fear-mongering.
Inappropriate fear-mongering. Let me just also point out, radioactivity is something that scares people, but it's much easier to measure radioactivity in a sense than it's almost any other pollutant. And so it's not hidden.
Especially compared to mercury contamination. Like I recently read that, a recent study that I took a look at of autism rates in proximity to coal-fired plants was just insane. And there's a lot to be parsed there. But these are long-standing heavy metal contaminants, and they're nowhere near as closely monitored or contained as you get from a nuclear reactor.
Yeah, absolutely. And there are lots of issues associated with that. I mean, I'm not an expert on the epidemiology of that, but there are lots of issues. I mean, aside from those subtle dangers, there's coal, the cancer rates. It's just the breathing, the respiratory problems, all sorts of overt things that happen. Now, fusion, it's been joked that fusion is 25 years in the future. It's always been 25 years in the future, and it'll always be 25 years in the future. And that's certainly been the case during my adult lifetime. Now, however, there is a big test fusion reactor being built in Europe, and sorry, and and so there's progress being made, but the question is, at what that progress is going to cost many, many billions or tens of billions of dollars to make this thing work. And the question is, at some point, the economics, even if you get it to work, will the economics allow you to build economically feasible fusion reactors versus using other things like solar power or conservation? It's always I think the major obstacles, once we have that technology, which we don't have, will be economic. So the reality that fusion may be 25 years in the future is a little more real now. But whether it'll be workable, if you ask me to guess, I would say it's unlikely we'll have workable fusion reactors producing a significant amount of power within 25 years. But it's worth the effort to look at it, because if you did, you have basically a virtually unlimited source of power without any either radioactive byproducts or carbon. So it's certainly worth the research, but I wouldn't hold my breath.
Okay.
Regarding policies of carbon. Well, that's an interesting question. It depends what country you have and what's happening. The United States policy toward climate change has changed dramatically with the new election. My only concerns are, it's great to not have climate deniers in essentially in power, and that's good. But one has to be careful to make sure that the people who are buying into human-induced climate change aren't doing it in a religious way, that they're basing their proposals and their statements on fact, which is one of the reasons why I wrote the book. I wrote the book for everyone. It doesn't talk about policy. It's just science, so that people can then say, here's the science. How can we make rational policies? That was my point. But, I do worry when people make apocalyptic statements about what's going to happen in 5 or 10 years as a way to scare people. Well, it does get people's attention, but I prefer in general policy to be based on reality, on empirical reality. And I think it's important when we hear statements about such, crazy things the problem with saying the world's going to end in 12 years, as some people on the left have done, is it's not. It's not going to, because of climate change directly. And to say that gives you the kind of boy who cried wolf syndrome. Mm-hmm. When it doesn't happen, people don't trust the science. And the point is that statement is not really a scientifically credible statement. So you want to make sure you protect the arguments and do it rationally, and also aren't misplaced. I remember in one of the Senate hearings for one of the Supreme Court justices, a senator who's now vice president, said, "Well, do you accept that climate change is going to affect the air we breathe and the water we drink?" And well, it doesn't really affect the air we breathe in that sense. And so, you want to talk about what the real things are about climate change and temperature change and sea level rise and possible other ocean acidifications and possible changes in ocean currents. And anyway, so bottom line is, I'm happy that there's movement in the right direction, and I will keep criticizing if I see statements made that aren't based on science, which is really my major concern. And the bottom line is, I'm more optimistic than I might otherwise be because of a generational thing. Young people have basically bought into the fact that climate change is human-induced, or rather there is a human-induced climate change. And once that happens, it's hard to slow the wheels, just as we saw with gay marriage. It didn't really matter what older senators or Supreme Court justices thought. Once a younger generation realized they had lots of friends who were gay and it was no big deal, the game was done, as far as that's concerned.
Well, fantastic. Okay, so I want to ask you a personal question that's near and dear to me that kind of tail ends on the end of there. I wrote a book about a catastrophic climate event called Hawks at the Diner. And in it, I go back to one of the earlier theories that was bandied around a lot during the 70s called the clathrate gun. Unfortunately, I didn't have enough time. I just found out about this AMA earlier today. I would have loved to read your book and be able to talk about it. Does your book go into some of the worst case projections for that? Are you following sort of the increasing rates of methane from Arctic melt?
Sure.
Yeah, I just wanted to. I know we just said, we can't talk about doomsday scenarios in 12 years, but I'm very interested in doomsday scenarios in a century or 2 centuries, where we start to see my own research. I came up with sea level rises in excess of, in some cases, 30 or 40 meters. I'm not a scientist though, so
Yeah,
take that
well,
with a
I would
grain of
say
salt.
that's
Yeah.
highly unlikely in the
Yeah.
next few centuries. But
Okay.
but the
What do
point
you
is
see?
that,
Yeah.
what I do, bottom line is I do talk about what you might call some close to doomsday scenarios. What I try and do in the book is sort of like, as I say, kind of like Charles Dickens.
Mhm.
The future as it going to be, and the future as it might be. Like Charles Dickens quotes Christmas future. Well, this is what it might be, but we can still do something about it. And as I say in the book, the future is charging at us like a freight train, but it's doing it on tracks that we've built. So there's some things we can do. So there are the simplest predictions are gradual and predictable, and they involve temperature rise. It could be can be well predicted globally. Sea level rise, acidification, and to some extent effects on currents like the AMOC current that may affect Europe and the east coast of the United States. And those things are real, and some of them are written in stone. The sea level is going to rise between a half a meter and a meter, no matter what we do, just because of the heat we've already dumped in the ocean this century. And so we have to live with that, and that's important. That's not trivial. A meter may not sound like a lot, although
That's a lot of fluid to expand. Yeah.
Well, yeah, it's really due to expand. Half of it is due to expansion. The other half is due to melting of glaciers and ice shelves. But a meter can seem like a lot if you have a bowling ball above your foot. And more importantly, a meter can seem like a lot if you realize, as I begin the book and end the book in the Mekong Delta, where I was traveling last year, almost all of South Vietnam, which produces one of the richest rice-producing areas in the world, is less than a meter above sea level. And so in the end of the century, you've got this question of what's going to happen to that region, and I go into it. So those, that's not trivial, and probably 190 million people around the world will be affected by that rise of a meter or a half a meter to a meter by 2100. So it's not trivial. There'll be a lot of climate refugees. There'll be some upheaval. Of course, we can do things about that. We can, even if we can't slow it extremely, what we can do is try and mediate it, and with technology and assisting poorer countries in infrastructure. But then there are the tipping points that you might talk about, the things where there's a lot of nonlinear feedback, where you might expect a sudden change, and I talk about that in the book. They're less certain.
Hell yeah.
Everything from, as you say, a catastrophic release of methane in Siberia and other places that where there's a feedback system that causes it to accelerate. Or if you want, just take the melting of Greenland, which is certainly happening at an accelerating rate, but we don't know can't really tell if that acceleration is going to continue. But we do know that there are certain effects that are highly nonlinear, like when the ice shelf melts, the top of the ice shelf is a mile above sea level at least. And when it melts, the top of the ice shelf lowers in elevation. But lower elevation is warmer. Mm-hmm. So that causes the ice shelf to melt faster. And that kind of nonlinear feedback is important. Plus the fact, I think it wasn't really recognized, but empirically it's been shown, that you might think as the ice shelf melts and more fresh water goes in the ocean nearby, that it would affect precipitation rates, and the snow rates would increase in some sense to work against that ice shelf melting. But it turns out what was observed in a few of those high ice melting seasons is it caused a local high pressure system over Greenland, and that high pressure system meant there was less snowfall than normal. And so that's another possible feedback. But then from there, of course, you have the melting of those ice shelves do two things. First of all, the melting of Arctic ice in the north, that's not changing sea level rise if it's sea ice, but what it is doing is changing the albedo of the Earth, because the water isn't white, and so it reflects less of the heat and absorbs more, and that's a nonlinear effect. Plus the fresh water that's going into the sea near Greenland, first it's warmer and it can affect the coastal melting of glaciers, but more importantly, it affects the salt content, which affects that's the thing that drives global ocean currents and can affect, and it's being observed now. Last 2 weeks ago, there was a paper that showed pretty definitively that there's some evidence of weakening of the AMOC current, which really drives the climate of the East Coast and Europe. So, and then of course from there, if that changes, you've got droughts in Africa and maybe a drought in South America, which if it turned the rainforest into savanna, you might think, well, okay, that's just a change, but the rainforests store an incredible amount of carbon. So if those things die off,
the earth,
there's more carbon. So there's all these nonlinear feedbacks, and you got to ask yourself the question. And yet they're all hard to calculate because nonlinear feedback is a much more difficult thing to do. So it's much more uncertain. But the way I like to put it is, it's like Clint Eastwood in those Dirty Harry movies, where he'd say, "You're feeling lucky, punk." You've got to ask yourself, how lucky are we feeling? Is it worth taking that risk? Or is it worth some preventative measures now, even if that risk isn't real but doing the preventative measures doesn't hurt us? Maybe it helps us by helping us develop new innovative technologies. Maybe it's worth doing now.
Oh, I love that. It's so metal to me just hearing about it. It's fantastic. I don't know if you cover sulfur hexafluoride at all in your book. Microsoft recently received a patent for data centers which use sulfur hexafluoride, a tremendously potent greenhouse gas. And just recently in France, we had the OVH data center burned down. They weren't yet using this new technology, but more and more we're seeing sulfur hexafluoride in industrial applications for electrical switching stations, and more in data centers, which are becoming huge sinks, just massive sinks of carbon and so forth.
Well, I think the point is, I don't discuss sulfur hexafluoride directly, although except it's in some of the graphs in terms of radiative forcing.
Yeah.
But the main thing to realize is that energy, that expending energy generally, unless you do something specific, produces carbon or greenhouse gases, and computer technology, the information technology, while it may not look like it's carbon intensive because you don't see the effects like coal plants or trucks or whatever, it use huge amounts of energy.
Yeah, it's massive.
Just recently, you've probably heard that Bitcoin, for example, people are talking about gigawatts of power that need to be used to basically associated with the cloud storage associated with Bitcoin. And so we have to recognize that we have to figure out ways to generate, energy production is associated with wealth in our modern world, basically. And so we have to figure out ways to ensure that energy production is done in ways that don't generate greenhouse gases. And that's possible, but it takes time to transition. But you're absolutely right. I suspect that Microsoft, I think that businesses are much more sensitive than they were to greenhouse gas production because they can't afford not to be, I think. And so that is a problem. But like ozone, I think, that's the kind of thing you can imagine a technological solution for.
Okay. Well, all right. Thank you for getting into that. All right. So a few people have been bringing this up. I do see your questions scrolling by on the screen and so forth. And it's something that you're well known.
I could.
No, it's okay. It's okay. We'll send you a copy of the video later if you'd like it.
Okay.
But this is you're very well known for having a very strong stance on organized religion. So this question comes to us from Mount Fuji, and it's a long one. I'm going to read the question in its entirety, and feel free to pick any part of it that you would like. Question: do you think the eradication of organized religion from society is naturally beneficial to the human race? Do you believe organized religion will naturally fade out of relevance, or do you think it's an indoctrinated enough system that action must be taken against it in order to reduce its societal influence? If so, how could this be done fairly and justly while keeping into account the rights of people's individual beliefs and the cultural relevance of religions? Is there a way to accomplish the diminished influence of organized religion while also preserving its cultural importance and not infringing on the rights of believers? Probably no. But this is a question about whether it's a noble idea to eradicate religion, if it will generally fade and lose relevance, or if direct action is necessary to reduce its impact on humanity.
Well, of course, as I often tell people, I hesitate to make predictions except for predictions 2 trillion years in the future, which are easier to make and no one's going to be around to check them. So
I'd love to know your prediction for 2 years, whether it's like Big Rip or whatever.
It's going to end badly, I can tell you that. But We'll maybe get there. But so look, I don't think you can enforce. I don't think you can, nor you should you enforce thinking. So, and my friend Noam Chomsky said that to me before. He doesn't care what people think; it's what they do that matters. Unfortunately, what you think affects what you do, which is my concerns about religion in the whole. So, I don't think it's ever good to legislate against religion. What you want to do is not legislate. What you want to do is ensure that nonsense doesn't dictate people's actions, and that actions are based on reality, on empirical evidence and reality and logical thinking. Now, there's so much evidence to suggest that religious thinking is probably evolutionarily hardwired in our psychology, and so it's really hard to get out. As Fox Mulder said, "I want to believe," and I think most people do. They want to believe the things they want to believe. And that's why science was developed. Science was developed because we all have that tendency, and the scientific process helps us overcome that natural tendency to think that what happens to us is special and that the world really is catering to us. And it takes time and effort, and science, and scientists often fail that test. So the process of science, of testing, retesting, questioning yourself, always be willing to prove yourself wrong as well as right. These things are not natural, and have to be, in some sense, regularly taught and among young scientists. So I think that there's a natural tendency to want to do that. I do think, though, that in the first world, you can definitely see traditional religions impact decreasing, and more and more Christians say they're Christians without believing any of the tenets of Christianity. Mm-hmm. They just, as it was in a recent survey and a census in England, when they looked at people who classified themselves as Christian, actually the Richard Dawkins Foundation had sent out a further survey and asked why, and asked if they believed, in all the things like transubstantiation and that sort of thing. And people said no, 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 no. And then the question was, why do you consider yourself Christian? And the answer is, I like to think of myself as a good person. Because religion is kind of usurp morality. If you don't say you're religious, and people think you're a bad person. And that is an unfortunate thing, because, of course, it's not true. And it's also not true that if you are religious, that you're a good person. And as I've often quoted and probably misquoted, and my friend Steven Weinberg's, who's a Nobel Prize-winning physicist and also an atheist, has often said, they're good people and they're bad people. Good people do good things, bad people do bad things. When good people do bad things, it's religion, more or less, is what he said. And I think that that's true, and I think we have to ensure that religion doesn't leak into the public's, into politics on the one hand, but also into the political arena, the public arena, in a way that hurts people. And I guess the most insidious negative of religion that I noticed, which I didn't really think about. I mean, I'd fought fundamentalists for years, and because they wanted to get rid of the teaching of science in schools and that sort of thing. But more insidious still, I think after our movie The Unbelievers came out, I got tons of letters and emails from people who say, I live in a small town in south of the United States, and I can't talk to anyone. I feel like a bad person for asking questions, about whether God exists, and I could never mention it. And I think that's the insidious aspect, that people are made to feel bad about something that absolutely everyone does. Everyone questions that at some point in their life. And we should encourage questioning of all sorts. So I think what we want to do, rather than put down religion, is rather encourage a worldview, first of all, that says the real universe is so fascinating that we don't need all the nonsense. And secondly, that encourages open questioning of anything. And that, by the way, not only is important for fighting organized religions, traditional ones, but modern religions like the religions of wokeness, that which say that certain topics can simply not be discussed. And that, to me, is just as dangerous. So I think we want to try and encourage open discussion, debate, and questioning. And ultimately, that will improve society. And whether it leads as an automatic byproduct to the demise of religion or not doesn't interest me so much. And we can also think of, well, what are the positive things that religion does? Well, it binds people together into community in some way. And what other things can we do to bind people together into communities in positive ways that don't involve fairy tales? And we can think of that. But as I say, it's not I'm not. I used to classify myself as an anti-theist after my friend Christopher Hitchens, my late friend Christopher Hitchens. But now the word I would use to describe myself as an apatheist.
Mm.
I really don't give a damn about God because God doesn't enter into my thinking and my work and anything else. And bottom line is, the world would be a better place if it didn't. I think if that kind of supernatural hocus pocus didn't enter into people's actions and in the public arena.
All right, thank you very much. So I want to be cognizant of your time. I know that you don't have much of it left. How long do you have left with us here?
Well, I in principle, I give you 45 minutes, but I'll give you 50.
Oh, all right, amazing right there. Okay, so Pragma Plot has a couple of relatively in-depth cosmological questions here. I'm going to
Okay.
ask with the one at the top, and if that one is into your liking, we could try the second one. So he says, the LIGO collaboration detected what they thought was the merger of black holes with a combined mass of 150 solar masses. Because of the odd masses of these black holes, there's been speculation that this event is actually the merger of boson stars, dark matter stars, or some other type of exotic matter. What's your take on this possibility, if you've been paying attention to it? And do you think LIGO... Sorry, you were saying?
Go on.
Do you think... Yeah, do you think LIGO and other GW detectors of the future will end up confirming the existence of these massive exotic objects, or will we never be able to tell the difference between these theoretical exotic objects and black holes?
Well, look, I think that I've read not so much LIGO, but there's another array that looks at timing of pulsars that is suggestive that low frequency gravitational waves, which seem to be a signal, and by looking at relative timing of pulsars, you can look for very long wavelength gravitational waves. And that simplest argument is that they're a merger of supermassive black holes. And then a lot of people have suggested other sources of gravitational waves. And I think I don't know whether you want to use what's the word? You want to just take I think the bottom line is the simplest explanation, if it gives good predictions, is probably the one you want to hold on to. There are lots of exotic potential sources of gravitational waves. What you in order to find evidence for that, I mean, extraordinary claims require extraordinary evidence. So what you want to realize is that if you're going to explain these things using some exotic hypothetical phenomena, which let's say boson stars are hypothetical, but there's no evidence that they exist, and similarly, so what you want to do is say, well, I want to look for a signal that is in direct conflict with what I predict of something that we know exists. Because we do know, I mean, even though more massive stars have been seen in black hole mergers than you might expect, there's a lot of fuzz in astrophysical predictions. And of course, you can also imagine smaller black holes being built up by collisions to being larger black holes. So they don't not even every 100 solar mass black hole comes from a primary star. It may have come from two smaller stars that produce two black holes that merge, because we've seen that. And so we don't yet know enough about the merger rates and everything else to rule out those possibilities.
So can I stop you there? The next question in the line by Josh Buck M, he is interested in what happens during the collisions of black holes that at the boundary layer during near-miss events. What happens when the gravity from the two black holes cancel out? Is there a possibility that the reduced gravity of a near collision of two black holes might allow some energy to escape?
Well, when you say cancel out, I mean, gravity doesn't generally cancel except for...
Well, equalize, I think, is probably what the word that he wanted. Yeah.
I mean, when the bottom line is that when two black holes collide, come close, like anything else, there's a disturbance of space-time and gravitational radiation is emitted. That's a true statement. And so, but the less catastrophic the collision, the less gravitational radiation that's emitted. So if they come close and scatter off, yes, there'll be some gravitational waves emitted. And if there's no accretion disk, then real matter will also collide and you'll have electromagnetic radiation emitted. And so, yeah, you'll always be able to emit some radiation in that regard, but you won't get the same kind of oomph or bang for your buck as you will with a full head-on collision.
Okay. Then from Poopty Whoopty, great, or Poopty Woody, He has a
Uh-huh.
question. If we figure out how quantum entanglement functions, outside of like the obvious like communication over vast areas of distance, what are some of the cool things that could result from such some mastery of this process?
Well, hold on. But the
Oh,
first thing is we already
sorry.
understand it.
Yeah.
No. The first thing is there's nothing unknown about it. It's a property of quantum entanglement. Is a central property of quantum mechanics, and it's understood. And it's not mysterious. I mean, it may seem mysterious. It is mysterious on classical levels, but it's not something that we need to understand in from a theoretical perspective in order to work with. Let me say. I mean, there's always trying to understand, interpret things in terms of observations, and that's a little hairier. But there's already efforts to utilize quantum entanglement in every stage for quantum communication, which allows you to communicate with knowing if someone's eavesdropping, because that quantum coherence will be destroyed in some sense. So that's a really important thing. To moving information around in a quantum computer, either a local one or one that's got different nodes in different places, and so for use in information transfer in possible quantum computers, and in possible eavesdrop-free communication, those are two huge things we can use for entanglement. We can't use entanglement, even though it sounds like we could. We can't use it, I'm sorry to say, for faster-than-light communication or any of those exotic things, because it just doesn't work that way.
Okay. Well, fantastic. So we're almost out of time, and I wanted to ask you like a slightly more like personal question here. While I was doing the preliminary research for this, you wrote that one of the reasons why you got so interested in astrophysics and cosmology was you read science fiction when you were younger, specifically Isaac Asimov and so forth. When I was like 9 years old, I met Ray Bradbury, and he changed my life completely.
Okay.
And I wanted to find out, could you give us some, maybe like 2 or 3 of your favorite books of that era? Are there any that are still with you that you still care about?
Well, look, I actually liked. Let me say, to make clear, the best books by Isaac Asimov that I liked weren't science fiction; they were science fact. They were his books about science. Those what really turned me on.
Mm-hmm.
I did read science fiction. I did watch science fiction, and my favorite science fiction writer at the time was a guy named John Wyndham, who was a and you may be dismayed to find out that John Wyndham's science fiction didn't involve wowie zowie technology.
No, I read him like Day of the Triffids.
Day of the Triffids.
I'm a huge fan. Yeah.
And so after I wrote the physics of Star Trek, I was invited on a lot of programs with some well-known science fiction writers, let me say. And what I came to realize, what makes good science fiction is not the science, it's the story. Mm-hmm. If it's not a good story, it doesn't matter. The science is in there sometimes in science fiction to help the story push forward and to think about possibilities. As Stephen Hawking said in the foreword of my book, The Physics of Star Trek, science fiction, like science fact, helps spur the human imagination. And I think that's the great thing. Thinking about what's possible, even potentially possible, is wonderful. And science fiction, you have a much greater latitude because it doesn't have to be practical, and it doesn't even have to obey the laws of physics all the time if the story's good enough. But it does spur your thinking about possibilities, and that's wonderful. But it's really the science is not a central part of science fiction. It's a story. It's the detailed stories of human or alien intelligence that get you to think about your own place in the cosmos and how it might change you. So the ones that I think fascinated me the most weren't space travel or necessarily alien stuff, although Day of the Triffids in some sense is alien, but it's just a comment that goes by. As much as recognizing the possibilities for human experience. That doesn't mean, I like Star Trek growing up, and that's certainly space travel. But I think it's just because I liked TV when I was a kid. Anyway, so that's my answer. I think what happened is I stopped reading science fiction when I discovered that science was much more interesting.
No, that makes me feel terrible as a science fiction writer. Okay, so no, it's totally okay. So I'd like to sneak in one more question, if I can, from Atheist for the Cause, and he questions thoughts about the de Broglie-Bohm theory. Why isn't it taken more seriously? And I must ask, can you please explain what this theory is if
Well, I
it,
don't. It depends what he
yeah,
means by debug. I mean, there's just those names are key figures in quantum mechanics, and I don't know exactly what he's talking about.
I don't know
Pilot
either.
wave theory,
Yeah,
maybe.
yeah.
The
Pilot
point is
wave
that
theory is, I think, what he's
yeah,
talking about. He
yeah,
mentioned that.
okay.
Yeah.
And so the idea is that quantum mechanics, which basically says there are fundamental uncertainties that you can never measurably overcome in quantum mechanics, and that there's no underlying classical theory that describes it. Classical theories just don't work. Classical mechanics just doesn't work. It breaks down. There are other ideas that maybe the apparent uncertainties and weird behavior of quantum mechanics could be due to underlying variables or phenomena that we can't measure but are there, so that you can have a classical theory that explains the apparent weirdness of quantum mechanics. And I guess, I mean, I have not spent a lot of time researching many of these, but the fundamental point is that I don't see the need to. The quantum mechanics, every experiment we can do, and there are some that are really important that could ask, are there hidden variables that are underlying what's happening here? So it's not just a matter of the universe being crazy, but just a matter of our limit of access to information, what's going on. Every one of those experiments that's been tried that can give a definitive answer validates that quantum mechanics just is the way it is. And so I've never understood, well, I guess I understand, but I haven't resonated with me this fixation that some people have with trying to get a classical picture that explains quantum mechanics, because it seems to me equally likely the world is quantum mechanical. And then the important thing is not the interpretation of quantum mechanics, but as a late friend of mine at Harvard once said, the interpretation of classical mechanics. We've got to understand why this world we see, which is an approximation of reality, how can we interpret that world in terms of the underlying reality instead of trying to explain the underlying reality in terms of some approximate world? But I may be selling pilot wave theory short, but it is bottom line is that I don't see it adds any in terms of my understanding of the world and ability to use quantum mechanics. It's never added anything. So I've never needed to worry about it.
All right. Well, we're about out of time here, and I wanted to give you an opportunity. First, like, I'm very interested in reading The Physics of Climate Change, which I understand is out now. It sounds fantastic.
Mm-hmm.
I want to thank you so much for coming to our Discord server. This has just been the highlight of my week, and I love that a lot of people got some great questions asked, and I've learned a ton here. And, not to get too maudlin about the whole thing, but yeah, thank you so much for this. And are there any closing thoughts that you have for anybody? Is there any advice that you want to dole out to somebody? There's a lot of young people in the audience, and if there's a book that you would love to have them read, maybe one of your own, maybe somebody else's, or something that you want to leave us with, I'd love to hear it.
Oh, well, I guess, I hate to give advice, but there's two things I like to say to young people. One is, don't forget why you enjoy what you're doing. And and do what you do because you enjoy it. Because if you don't enjoy it, you're not going to be good at it. So sometimes, if you're interested in physics, the first year of physics can be tedious. But don't forget that at the end there's light at the end of the tunnel. So just keep have the courage to keep doing what you enjoy doing, and that should help govern you more than worrying about a job down the line or other things. And the second thing I always say is, don't let the bastards get you down.
That's fantastic.
So I guess that's
all right.
it.
Well, thank you so much. And everybody who participated in this, I want to thank you for asking questions. I'm sorry that we couldn't get to every single question that was here, but you've been very generous with your time. I think if you have a chance to speak with Mighty Thor on your way out, he'd love to talk with you about the whole situation. And
sure. Yeah. And let me say, I enjoyed it. Thank you for moderating so well and politely. And I'd be happy to do it again. The questions were interesting, and obviously, I've written 11 books, so the new one is a new one. But if you're a Star Trek fan, the physics of Star Trek. Even if you're not a Star Trek fan, I wrote that. But it's accessible, and the Universe or Nothing, which I think really addresses that central question. In some sense, why are we here? But anyway, thank you. I enjoyed it, and I'd be happy to do it again sometime.
Great, superb. All right, everybody, that is a wrap on this. I'm gonna continue broadcasting on this channel for the remainder here, and then I'm gonna try and set up Mighty Thor and everybody. Yeah, great job with some of these questions. I learned a. All right, whose dog is that?
Yeah, my dog is thanking everyone too.